All right. So today we're talking about elastic potential energy, which is anything with a little bit of elastic in it. Springs, rubber bands, bungee cords. Actually, most ropes have a little bit of elasticity in it. It kind of depends.
In your socks.
Your socks?
Yeah. Stretchy part right here.
The elastic in your socks?
Mm-hmm.
Yes, the elastic part of your socks is elastic. We talked about gravitational potential energy as being UG. So elastic potential energy is going to be us. It's potential energy of a spring. Energy stored as a result of a force to deform an elastic object. In this instance, deform means to change the shape of. We talked about on Friday that potential energy can be due to like the position, like the height for gravity, or it can be the position of its pieces. In this case, it's talking about that deformation of a spring or the part of the bow that you pull back on, whatever it happens to be. Okay, the amount of elastic potential energy stored in such a device is related to the amount of stretch of the device. The more stretch, the more stored. A force is required to compress a spring. The more compression there is, the more force that is required to compress it further. This also goes in the opposite way if you're elongating that spring, if you're bringing it apart, which is what we're going to do tomorrow. So there are two formulas associated with this. The hard part is remembering kind of which letter goes with what. So the force of a spring is K times X. And the potential energy of the spring, which remember we really do US, is going to be 1/2 times K times X squared. Please remember that there's a difference between squaring something and multiplying it by 2. So K is our spring constant. It's going to be the amount of give in that spring. And X is the distance deformed, the distance changed in the spring. All right, as far as units, forces are always in Newton. X is going to be in meters, and K is going to be Newton per meter. Newton divided by meter. Joules, the others are the same. All right, Hooke's law states that for certain elastic materials, force is proportional to the extension when a sample is stretched. That means as you pull on that spring, you're going to get expected values. If you're to graph it, you get a nice straight linear line. It's not random. It's not it doesn't quadruple or triple or anything like that. However, no sample follows Hooke's law indefinitely. The elastic limits can be reached. This means the sample will no longer return to its original shape when the force ceases to be present. You see this if you wear elastic pants on Thanksgiving dinner. Sometimes they're just a little stretched out afterwards. Eventually, the force will become so great that the material snaps. That is your work pants after Thanksgiving break, where they ain't going back. The elastic in them has snapped and it is no longer stretchy. This is called the yield point. You do not want to get the yield point if you're like bungee jumping. That would be when the bungee breaks because they didn't use the right one on your weight. Which is why I don't bungee jump. Among other things. Any questions on this? It's pretty straightforward. The hard part, like I said, is keeping K and X separate. Okay, look at your worksheet for today for me. We're going to change a few things on here.
Get over it.
You okay? I feel like you need it.
No.
Okay. I feel that. Air hot?
No.
Fist bump? We believe in easy math, so our gravity on Earth is going to be 10 meters per second squared. Bring this out over here. Weight is a force. Write it down. If it gives you the mass and you need to solve for K or X, weight's a force. You find the weight of that mass, which would multiply by 10 for gravity. That becomes your force, which you can use for your Hooke's law. We good? On the back, number 12. It asks about the proportionality constant. That's really just asking for the spring constant. Remember how we said it was proportional? And that's pretty much it. So just because I'm on the back, I'm going to do number 11 real quick. It says a 25 Newton force stretches a spring 280 centimeters. What's the spring constant? F would be 25 newtons. X would be 280 centimeters. Ooh. Which I need to make into meters because of our SI units. So how many meters is 280 centimeters?
28.
Okay. Stop. Just run. Nope.
2.8.
Remember, kids have dropped over dead converting metrics. We're at centimeters. We want to be right here at our base unit for meters. 1, 2 times, move that decimal. 1, 2 times would be 2.8 meters. Love you guys. So F equals K times X. 25 equals K times 2.8. How do you get K by itself? Divide both sides by 2.8. 25 divided by 2.8 is going to give me what? 8.9 Newton meter. Make sure you put your units on there, and that is all she wrote. Should have no problems finishing this.